So we have constructed UQG as a Hopf algebra. And therefore, rep UQG, the representation category of that algebra, is a tensor category. And also, if I restrict to finite dimensional modules over that, it's a tensor category with duals. I told you also a little bit what happens if you set Q to be equal to a root of unity. You have a few weird things with Weil modules that are no longer irreducible. But we actually need to understand a little bit better the structure that exists for generic Q before we can go on and analyze what happens when Q is a root of unity. And the structure that I'm going to be focusing on for this lecture is the R matrix, which exists. Well, you first need to construct the R matrix when Q is not a root of unity, and then you need to worry a little bit further to see what happens if I set Q to be equal to a root of unity. And it's good to do things in that order. So for the moment, Q is not a root of unity, and later we'll see what to do in order to make Q be a root of unity, because that's the case that actually interests us. So we want an R matrix which will make this into a braided tensor category, as was explained by Chris this morning. So how does one construct an R matrix? A priori, it's difficult. The equation that you need to solve is something that is not possible to just go and write down and then try to find a solution. It turns out that for the case of this particular Hopf algebra, there's a trick that will build an R matrix. And the trick is to note that there is a Hopf pairing between the following two subalgebras of UQG. So recall, B is the Borel subalgebra. That's the algebra generated by the H's and the E's. So B plus. B minus is generated by the H's and the F's. So you have all the Cartan subalgebra, all the H's, and then raising operators. That's this. And then the Cartan and all the lowering. That's B minus. Oh, and that's not quite true. You need to modify the coproduct on this one and put the opposite coproduct. And I'll denote it by op with a little bar. Chris and I had an argument yesterday as to what is the best notation for this, and somehow we concluded that all notations are bad. So I'll use a bad notation which is different from Chris's favorite bad notation. Anyways, so this means opposite coproduct. The product is the same. The coproduct is switched. So let me tell you first what a Hopf pairing is in general, and then I will explain how the existence of a Hopf pairing can produce an R matrix, and later I will construct the Hopf pairing between that and that. So, suppose A and B are Hopf algebras. Then a bilinear map from A and B to C, well, to the ground field. It depends what the ground field is. If we're doing UQG, the ground field would be C adjoint Q. Now I'm doing it in, well, okay, here, ground field. Okay. Over K, a field. So this thing is called a Hopf pairing. If it satisfies certain axioms, which I'll write down. So the pairing between A and the product of two elements of B should be equal to the pairing between the coproduct of A and the tensor product of two elements of B. Similarly, on the other side, A1, A2 paired with B is A1 tensor A2 paired with a coproduct of B. So that's saying that the product on A is dual to the coproduct on B, and the coproduct on A is dual to the product on B. Then we need similar conditions for the unit and the co-unit. So A paired with a unit element of B is epsilon of A, and the unit element of A paired with any element B is the co-unit on B. And then finally, I need to explain what I mean by this notation. And this is a pairing between A tensor A and B tensor B. What is that pairing? So A tensor A So this pairing induces a pairing like that by declaring A tensor A prime, B tensor B prime to be equal to A B A prime B prime. So I use this definition to make sense of this condition. Same thing here. That's a Hopf pairing. So let's believe for a moment that there exists a Hopf pairing between those two algebras. Then I can write down an R matrix. It goes as follows. Take a basis of this algebra, call it E lower p, and take the dual basis of that other algebra and call it E upper p. And I'm not writing this opposite coproduct there because, well, the notion of dual basis just cares about the underlying vector spaces and the pairing. This is, so suppose we have such a pairing, then you write that. And then the claim is that this expression, sum over all basis elements, yes?
How do you make sense for this sum? In fact, these are infinite bases.
There are infinite dimensional algebras, and therefore you need to worry about what this means. So, okay, very good question, and actually, it's difficult to make sense of it. If A and B were finite dimensional Hopf algebras, then you could write that, and then there would be an easy proof that this is an R matrix. So I'm going to present that in a moment. I'm going to say why, formally, it satisfies the equation. Later, I'll go back to the example and say, okay, now we care about this and about that. Let's try to write down that thing explicitly and see if we can make sense of it. And we will realize that we cannot make sense of it. It just looks like it's an infinite series that diverges in some sense. And then you sort of need to do some dirty tricks. You're like, okay, well, let's then do a few things. And eventually, sort of by being inspired by this formula, you end up with another formula that then is something that makes sense and is an R matrix. So, yeah, it's tricky. But let me now pretend that there's no issues and prove this proposition under this assumption. So first of all, here we have bases. So since we have bases, we can write everything in terms of bases. In particular, we can write the product and coproduct in terms of bases. So let's write the product of two elements of, so lower indices means that I'm an UQB plus. The product is going to be, well, some combination of, and then a coefficient that I call mu PST EP. There exists a matrix such that this is the case. And the coproduct of EP is going to be some other matrix. And now things look as follows. Nu ST P ES tensor ET. Because these two algebras, the duality is a Hopf duality between these two things, the matrices that control the product and coproduct in that second algebra are the same as those matrices, except they play opposite roles. So we also have ES, ET equals sum over P, nu PST, EP. So that's encoding that. Let's see, which relation is that encoding? That's a coproduct on the second algebra. So it's encoding that relation here. It's the product on the second algebra. So it's this relation here. Okay, and now we have the last one. Delta of EP is sum over ST And, well, there's this little trick of having the opposite coproduct, and that's where you see it. So that's what we have. We have two bases satisfying these four relations, and also these relations here that are somehow less important for this computation. So now I can give a proof, a formal proof of that proposition. So we need to check the following identities. So the identities that I want to check these are the identities that I want to check, and Chris mentioned in his talk that there was a small mismatch between conventions of what we use as R matrix, so apologies for that. But anyways, so let me start with the first one. Well, I put in the definition of the R matrix. We get that expression. Now I put the definition of the coproduct. I get a summation over three things now. Very good. Now we recognize this combination, nu STP EP, as something that appears here. Then we can go back there. So the summation over P disappears. Summation over S and T only. ES, tensor, and now the product. Did I do things wrong? I did things wrong. ST. What am I doing? ESET. No, that's good. Very good. Well, and that is exactly the meaning of that right-hand side. So it's really easy. So R13 is this copy of R that is indexed over S. It appears in 1 and 3. And then that copy of R that is indexed over 2 and 3 is the one that we use the summation over T. And that one appears on the left of that one. And you can see that here. So, OK, so because it's so easy, I'll do also the other one. OK, we go on. Triple summation. Now I use mu, because that's the coproduct in that algebra. ST is good, but I need to use TS. That's exactly what I try to emphasize over there. And then that's a sum over ST. Now it's ET, ES, because they show up in that in the other order. And that is exactly what you want. So it's just super easy. Okay, so as I said, there's issues in making that construction work because these two algebras are infinite dimensional. But before thinking about those issues, let's just write down the pairing between these two things. And then at least we know what we're talking about. So okay. So I'm going to give you this pairing on some generators. EI, FI is 1 over. So DI, these are these numbers that are equal to 1 when it's when I corresponds to a short root, and equal to 2 or 3 when I corresponds to a long root in the Dinkin diagram. So it's like, so if you recall, say here I draw F4, the numbers DI are equal to 2, 2, 1, and 1. Okay, so that's what you have. The pairing between Ki and Kj is the pairing in the root lattice of these two in the weight lattice of these two simple roots. Well, Q to that thing. And all other, so let me be more precise, all other pairings between the EIs and the FIs and the KIs are 0. I'm not saying that everything is 0. Like pairings between elementary generators are 0. As a general rule, this pairing is compatible with the grading by the weight lattice. So the only possibility to have something non-zero is if the weight of this plus the weight of that are 0. So for example, if I have EI here and FJ there, where J is not equal to I, the weights don't add up to 0, and therefore there's nothing. Yes?
Are you extending the pairing to the entire UK? Because
yeah. So
when you say any other pairing is 0, it seems that you are extending to the
any other. So the things that I claim are 0 are EI FJ, EI KJ, and KI EJ and KI FJ. These are the things that are 0. There's nothing else that I'm making a claim about. And as we'll see, there's many things where you get non-zero. For example, EI squared paired against FI squared, that's going to be non-zero. Yes?
What about the inverses of the KIs? Are those also 0?
No. If I put here an inverse, I get a minus there. But those are actually forced by. If I put one inverse here, I get a minus. If I put an inverse and also an inverse there, I get a plus. So I claim that this information is enough to determine this pairing up here. And actually, that's a very, I mean, I say it, but you shouldn't believe it. This is something that is not something that you expect to be enough to give just on the generators. Let me show you how it works in a simple case, in an SL2 case, to see how you can derive the value on, well, I'm going to do E squared paired with F squared by using those formulas over and over in an inductive way. And then you'll see that, well, the fact that this inductive procedure terminates is kind of, it feels a bit like luck. It feels that in other examples of other Hopf algebras, it might not terminate. Okay. So in SL2, UQ SL2, the pairing is the following. EF equals 1, EK equals 0, KF equals 0, and KK equals Q squared. So that's what we have. And now say I care about E square F square. And I'm just taking this example because it's not too complicated and also not too trivial. So we use the rules that we have. So F square is a product of F times itself. So I can use this first rule to say that it's the coproduct on E squared paired with that. The coproduct on E squared is, because delta is an algebra homomorphism, it's the square of the coproduct on E. Now I'll write it out. So E tensor K plus 1 tensor E, E tensor K plus 1 tensor E, paired with F tensor F. You already get a feeling why you don't want to do expressions that are too complicated. Anyways, this one actually can be done in a reasonable amount of time. So let's push on. So I'm going to cheat a little bit and already use what I told you about degree reasons and things that end up being 0. So for example, if I look at this term times that term, that's E square tensor K squared, that doesn't have the correct by degree to have something non-trivial with F tensor F. So I'm not going to even write it down. I'm going to pretend that I've already checked that this is 0. So what I'm going to write down is this times that, which produces E tensor KE, and then that times that, which produces E tensor EK. Okay. Let's see. We have this factor E tensor F in the beginning on both places. So we can put it in front. But E tensor F is equal to 1, so we can remove it. So it simplifies to simply KEF plus EKF. Okay, well, we started with something as a product times something with something that's a product. Now we've got rid of the product on one side, but we still have a product on the other side. So we start again. So that is going to be K tensor E times the coproduct on F. Well, for degree reasons, I only need to care about one of the terms of the coproduct on F. And the one that I happen to need is 1 tensor F. And here we have E tensor K, and same thing. But now the term that I need is the other term in the coproduct on F, which is F tensor K inverse. Again, I have this E paired with F that can go away. So that is K paired with 1 plus K paired with K inverse. K paired with 1, we use that formula. That's epsilon on K, which is 1. This guy here, I'll give you a little exercise, which is to check that K to the N paired with K to the M is related to K paired with itself by taking that number and raising it to the power N times M. So it's Q to the 2 N M. Okay, using that, we compute that this is Q to the minus 2, and we end up with 1 plus Q to the minus 2. Okay, great, we have an answer. Let's stare back and see what have we used in this computation. So you start with something that's a product paired with another product, and then you say, okay, we use one of these, and we write this in a simpler way, and that one in a more complicated way. You sort of trade difficulty. And then you expand this thing. You write it like that, and then you write it like that. Suppose the coproduct was a crazy coproduct, where each term had a coproduct that was like much more complicated than the term itself. Then this procedure would be starting with something simple and producing something more complicated from it. And then you do the procedure on the other side, and then you simplify that side, and that side becomes so much more complicated, and you never end. So the fact that this procedure terminates, depends in a very subtle way on the particular form for the coproduct. The fact that the coproduct of E does not involve anything that's more complicated than E. It involves E and K and 1 and E, and these are of the same level of difficulty or sometimes less, but not more. So anyways, this is just an example of how you compute things, and maybe it's believable that this produces an algorithm that is effective. You can just do it. If you care about E to the N times F to the N, well, if you have enough patience, you can just do it. And if you're a bit clever, you can even find a closed form for the answer. And I'll give you the closed form for the answer, because I'll need it later. So if the exponents are different, you get 0. That's for degree reasons. And then if the exponents are the same, what you end up getting is sorry, I'm mixing t's and That's what you get. You get a quantum factorial shifted by some power of q. So the quantum factorial, if you write it as a Laurent polynomial in q, it's symmetric. It has the same number of positive powers of q and negative powers of q. So for example, quantum factorial for 2 is q inverse plus q. And what this does is it shifts it and puts it all in the negative things. So you have a constant term and then only negative powers of q. So this is actually secretly q inverse times quantum 2 factorial. But, I mean, you couldn't have really guessed that from this computation. So let's go back to this expression. We give ourselves a basis of those two things, and we compute the pairing. So the basis consists of expressions of the form k to the n e to the t, and on the other side, k to the m f to the s. And the answer turns out to be just the product of this and that. So n runs over the integers, t runs over the naturals. And same thing for here. So that's just a computation. You can do it. It's a bit painful. If you already know the answer, it's easier because you can use induction. If you don't know the answer, you need to do a whole bunch of these and then get a feeling of what it might be, and then you can apply what I said before. Very good. So we have a basis here, a basis there. We know what the thing is. It looks like we're in good shape, at least to write down this formally. But actually, we're not in good shape, and we cannot write this even formally. And let me explain why. Well, suppose I want to use this basis here. Then I need to compute the dual basis. What does that computation involve? It involves inverting a matrix, inverting an infinite times infinite matrix. The contribution coming from the e's and the f's is actually okay, because as far as they are concerned, I mean, this viewed as a matrix indexed by s and t, that's a diagonal matrix, and that's okay to invert. So let's focus on this here. That's a z by z matrix whose entry in the column indexed by the row indexed by n and the column indexed by m, the entry is q to the 2nm. It's a z cross z matrix, and you want to invert that. Well, good luck. I mean, this is not something that is at all invertible. There's no way of making sense of how you could possibly invert this matrix. And so we're stuck even before being able to write this formally. So that's a problem. Okay, so what's the way out? The way out is to try something else, and because we still want to find dual bases. So the idea, so problem, the matrix Q to the 2nm indexed by Z is not invertible in any sense. I mean, and even if I could write down something that I claim is the inverse, I could not multiply the matrix with its inverse because they're infinite matrices. So it's really a problem. So the idea is go back to these other guys, the HIs, the ones that come from the classical Lie algebra. So they're related by Q to the DI HI equals KI. Remember when I was talking about these as being functions on the weight lattice. So these were just functions, and they're related by that equation. They don't really live in the algebra we care about, but let's not worry about the fact that they don't live there. Let's just try to compute this expression where we put h's instead of k's and see what we get. See if it's at all possible to get something that makes sense. So this really feels like it's a complete shot in the dark. First of all, there's all kinds of reasons why this whole procedure shouldn't be able to work. And then we have this pairing that exists on this algebra when you want to evaluate it on an element that's not even in the algebra. The remarkable thing is that it works. So let me show you how to make it work. And again, I'll do the SL2 case because there's enough complications in the SL2 case that there's no need to do the general case. So we want to compute so I mean, in SL2 case, there's only one H. We want to compute A. That's the typical thing that physicists do. They write something that a priori doesn't make sense, and what they want to do is compute it. So we want to compute that. So here's what we're going to do. We're first going to assume A is given, and then compute that expression in terms of A, as a function of A. So, well, that's his whole procedure applied to that situation. Let's see. OK, I'll do it fairly quickly. It's the mth iteration of the coproduct applied to h to the n, paired with the mth iterated tensor product of h with itself. That I can write as a sum over I equals 1 to m of 1 tensor h somewhere in the middle. So that's the mth iteration of delta applied to h. Well, all that to the power n. And then that doesn't change. Without loss of generality, we could have assumed that n is smaller or equal than m. So, well, let's see. If n is strictly smaller than n, then what do we have here? We have, how many terms do we have there? We have m spots. And we're taking this to the power n. So that's producing n h's that can come in some of these spots. If n is strictly smaller than m, then among those m spots, there's going to be at least one that's empty, that just has a 1. And this will produce, at the end of the day, a contribution which is this. But that is epsilon of h, which is 0. So we learn that it's 0 if n is strictly smaller than m, because of the argument I just told you. If n equals m, then again, you can sort of do the combinatorics. These n copies of h need to come in all the n spots available. They can do that in n factorial ways. And then you have the nth power of h tensor with itself. And you end up with n factorial times a to the n. That's when n equals m. Very good. OK, so we started with an expression for this, and we ended up with an expression for that. What we want to relate it to is to the information we have, namely that. So we just go and I can leave the let's compute. Well, so now we're going to do k paired with k, but we're going to compute it using this. We're going to say, I'm going to use this to compute that, and also use this and that to compute that, and then check it against that to eventually find the value of a. So it just so we write it all formally without really worrying about what things mean. So that's log q to the n divided by n factorial hn paired with log q to the m divided by n factorial h to the m. Well, that's what it means to take the exponential. It's q to the something that's the formula. Well, we know that the formula involves a Kronecker delta. If things are different, you get 0. So this is actually a single summation. We have a log q to the 2n divided by, we have this n factorial that cancels with that n factorial. So that's a single n factorial. And then, well, let's see. Let me do it in 2 steps. N factorial squared. So it's a to the n. And we can rewrite this as an exponential of this weird quantity log q squared times a. But we can also rewrite it as an exponential of something a bit less scary. We can rewrite it as q to the log q times a. Okay, that's kind of still a bit bizarre, but we don't worry about it. We just compare this with that and conclude that a equals two over log q. Great. So we can go back and rewrite the final answer for this pairing here as hn hm is delta mn n factorial 2 over log q to the n. Good. So we have a formula. Now, let's go back and so this is the place where we had left things. We arrived at this formula, and then we were stuck. So now let's start over and do it with h's instead of k's. So if you do it with h's, you end up with the following alternative formula. Thank you. Delta nm, delta st, n factorial 2 over log q to the n, q to the minus, t choose 2, t quantum factorial. Great. The big formula. What's good about it is that now, if you look at the matrix that is encoded by that formula, it's a diagonal matrix. There's like a Kronecker delta here and a Kronecker delta there. And therefore, it's possible to invert it and write down, formally at least, the dual basis to that basis. It's not really a basis because these are not elements of the algebra, but you can just write it down. And what you end up with is a formula for R. So let's see. This is A. This is not Q. Let's be. OK. Well, so we can start here and write down a formula for the R matrix. So, yes?
I don't want to be so much picky, but do you want to sum over, I mean, your n and m's, are you consider them to be integers now? Or?
Oh, yeah, it's changed. So now n, m are integers, and st are also integers. So here it was a basis indexed by Z cross N, and now it's a basis indexed by N cross N. And whether or not it's a basis, that's a subject of discussion, since the elements aren't really even in the algebra. Let's see. Okay, so we take that recipe and use that formula, and we get the following expression. Sum over n and t So I'm inverting that matrix. If you notice, all the expressions that were like in the numerator end up in the denominator here. And very good. So the dual basis to the basis of these HNs e to the t is the basis of these that times Hn f to the t. So I just wrote down this thing. Now let me massage this expression a little bit to bring it into a more palatable form. So first of all, I'll write it like this. I mean, this is where you see that why I chose to only do the SL2 case. I mean, you can imagine that same formula with, in the general case, you have like more summations, and it's not much more technical, but it becomes notationally very heavy. Okay, so we have that expression, and then what do? We're like, okay, summation over n, 1 over n factorial something to the n. We can rewrite it as e to the something. Oh, that something has a log q in the middle. That log q goes away. And then we rewrite it as q to the 1/2 h tensor h. Summation now only over t. Q to the this, 1 over the quantum factorial, et tensor ft. So that's a great formula. So let me rewrite it once more. So actually, what one should do at this point is go back and analyze that formula and see whether or not it is an R matrix. The proof doesn't really apply. It applies, I mean, you need to go back and check that nothing went wrong. Maybe one comment about how to make sense of these things. It's possible to complete this algebra so that both k's and h's live in there. So that's possible. And then these things are no longer bases, but they're bases in a topological sense, in the sense that finite linear combinations are dense in there. And so then the argument actually has an ambient hole in which the algebraic computation has a home, has a thing in which it happens. And then you need to worry about, well, it makes sense. You can make sense of it by being careful about completions. This thing here is not quite an element of the tensor product of this Hopf algebra with itself, but it lives in some completed tensor product of a completion of that algebra. So if I replace this algebra by some completion, then this really lives inside the tensor product in the appropriate sense of that algebra with itself, and so it really is an R matrix. Another way of saying it is to say, well, I don't want to complete things, and I don't want to then you lose the fact that this is an element of the thing times itself. What you still have is that it makes sense to act with this guy on any, if I have two modules, A and B, it makes sense to act on A tensor B. And that's essentially all you need in order to build a modular tensor category. So there's a couple of ways of making it formal. But there's one important point that I would like to make before I finish. Our goal was to do something where Q eventually is allowed to become a root of unity. And let's look at this formula. That formula has a very big problem. And the problem is that it involves dividing by a factorial. And when Q is a root of unity, then if Q squared to the L is 1, then quantum L is 0. And quantum L will happen at some point because that's a quantum factorial. So at some point you will have divisions by 0, and those are bad.
But then you have a finite dimensional U, because you have only finite bases, you can cut off the Howard power, high powers of E or F or K.
That's one solution, and that's not the one solution that I'm going to present right now. There's a way of doing it without what you're talking about is this so-called small quantum group. But this is not what I want to talk about. I want to talk about another way of dealing with that issue. So what you do is, let's see. You introduce well, let me do the SL2 case. You introduce new elements that are divided powers that are e to the r divided by r factorial. And you introduce them as formal new variables, new generators, and same thing for the f's. And these are subject to the relation that EI divided power by R, well, sorry, I'm not doing the I's. S is, well, you just figure out what it's supposed to be, and it's a quantum binomial. So you introduce a whole bunch of new generators, infinitely many generators, and these relations that govern them. using those generators, you can go back to that formula. I mean, you need to check that you get a Hopf algebra. That's a non-trivial thing to check. But using those generators, you can rewrite it in the following other way. Well, we gain a quantum t factorial from this one and a quantum t factorial from that one. So the t factorial is now in the numerator. And I have a divided power here and a divided power there. So actually, we're doing something rather drastic to that algebra. We're replacing that algebra that had finitely many generators by a new algebra that has infinitely many generators, subject to infinitely relations. And that new algebra is denoted the restricted quantum group, URES. And that algebra is an algebra that's OK to specialize at root of unity. And then you get the R matrix also specializes OK at root of unity. And well, it has been, I mentioned that you can complete it. So you end up with something that's really a Hopf algebra, well, in the topological sense, in the completed sense, with an R matrix. And that whole structure can be specialized at root of unity. It's still a Hopf algebra at root of unity. It's still an R matrix at root of unity. I mean, there's lots of things that you need to then go check. You need to go back to the modules and say, well, do the modules that we had analyzed before, all these Weil modules, tilting modules, do they look the same now that I have these new generators? And the answer is more or less they look the same. I mean, there are some small differences, but essentially they look the same. The theory is the same. And we haven't really changed too much. OK, so that's where I can stop.